You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Artificial intelligence agents can be defined as systems that combine perception of tasks, structured planning, and autonomous execution of actions in order to complete goals that would overwhelm simpler models. Unlike chatbots that generate single responses to prompts, agents are designed to sustain multi-step workflows, reasoning through each stage and calling upon tools or services as needed. The defining feature of agents is autonomy. Once given a high-level instruction, they do not merely provide a suggestion but actively chart a course of action, carry it out, and return results. This requires them to bridge the gap between language understanding and operational behavior. They are not only answering questions, but also managing processes, sequencing steps, and adapting dynamically as conditions change. In many ways, agents resemble junior colleagues. They need supervision and guidance, but they are capable of executing significant portions of work on their own. The plan-execute loop is central to how agents function. In this loop, the system begins by creating a plan, whether as a reasoning chain, a structured task list, or a decision tree. It then proceeds to execute each step, calling tools, retrieving information, or performing calculations as required. After execution, the system evaluates the outcome, asking whether the goal was achieved, whether errors occurred, and whether adjustments are needed. This evaluation feeds back into the next round of planning, forming a continuous cycle of thinking, acting, and reflecting. The plan-execute loop is critical because it prevents agents from drifting aimlessly or producing one-off actions without coherence. It anchors their behavior in an iterative process, giving them the chance to recover from mistakes and refine their strategies over time. Hierarchical agents expand on this concept by dividing responsibilities across levels of abstraction. A higher-level manager agent may be responsible for defining the overall goal and breaking it down into sub-goals, while lower-level executor agents carry out specific tasks. This mirrors human organizations, where executives set direction, middle managers allocate resources, and teams implement concrete steps. Hierarchy provides scalability, allowing complex goals to be managed without overwhelming a single reasoning process. It also improves oversight, since higher-level agents can review progress and adjust strategies. However, hierarchy introduces its own challenges, such as ensuring communication between levels remains clear and that accountability is preserved across layers. Still, hierarchical structures are becoming an important design pattern for deploying agents in environments where goals are large and tasks diverse. Task queues provide the organizational backbone for many agent systems. Instead of juggling tasks in an unstructured way, agents maintain ordered lists of pending items, each representing a step in the workflow. As tasks are completed, new ones can be added, reordered, or discarded, depending on the evolving plan. This queue system makes workflows explicit and traceable, allowing both humans and machines to understand the state of the process at any moment. It also enables prioritization, ensuring that urgent or high-value tasks are addressed first. In essence, task queues transform abstract planning into operational management, keeping agents organized as they execute complex goals. They are not just lists, but dynamic structures that represent the evolving logic of the agent's decision-making. Comparisons with simple models highlight the unique capabilities of agents. Traditional models respond directly to prompts, producing outputs in a single step without memory or follow-through. Agents, by contrast, sustain reasoning over multiple interactions, calling tools repeatedly, managing dependencies, and adapting to feedback. The difference is like that between a calculator and an assistant. One provides an answer instantly, the other manages a process. This distinction underscores why agents matter. They are not designed to replace simple models, but to expand their scope, enabling workflows that cannot be solved in one turn. Without agents, language models remain reactive. With agents, they become proactive, capable of carrying forward plans that span time, tools, and tasks. The benefits of agents are substantial. They allow automation of workflows that previously required human coordination, such as processing customer service tickets, compiling research reports, or managing IT operations. They free human workers from repetitive steps, allowing them to focus on higher-level decision-making. Agents also enable new forms of collaboration, as they can sustain dialogue, manage context, and return structured results over extended sessions. In enterprises, this means transforming AI from an advisor into a participant in operations, bridging human intent and machine execution. For end users, the benefit is often greater reliability and convenience. Agents can complete goals that span multiple steps without the user having to reissue instructions at every stage. Yet the challenges of designing agents are just as real. Multi-step workflows are fragile, and small errors early in the process can cascade into large failures. Stabilizing plan-execute loops requires careful tuning, robust schemas, and extensive testing. Agents must also balance flexibility with predictability. If they adapt too much, they may behave unpredictably. If they adapt too little, they may fail to handle real-world complexity. Debugging agents is particularly difficult because their decisions emerge from reasoning loops rather than fixed code paths. These challenges make agents exciting but risky, powerful but not yet mature. Building agents that can actually ship requires both technical innovation and organizational patience. Reliability concerns are at the core of agent deployment. Unlike simple models which produce static outputs, agents must handle uncertainty, errors, and unexpected conditions during execution. A tool may fail, data may be inconsistent, or goals may shift midstream. Reliable agents must anticipate these contingencies, incorporating retries, fallbacks, and error detection into their loops. They must also avoid spirals, where repeated failures lead to infinite loops or runaway costs. Reliability is not just about correctness, but about resilience, the ability to continue functioning in the face of inevitable imperfections. Without reliability, agents risk being impressive in demonstrations but unusable in production. Observability is another requirement for agents, as their reasoning and tool use must be tracked closely. Logs, dashboards, and monitoring tools provide visibility into what decisions were made, what tools were called, and what results were returned. Without observability, errors remain hidden and trust erodes. With observability, developers and organizations can understand agent behavior, diagnose failures, and improve performance. Observability also supports accountability, ensuring that when agents are used in sensitive contexts, their actions can be traced and explained. This transforms agents from opaque systems into transparent collaborators, capable of being audited and managed responsibly. Scalability is the next frontier for agents. Running one agent for one workflow is feasible, but deploying many agents across an organization demands efficiency in orchestration, resource allocation, and monitoring. Large-scale deployments may involve hundreds of agents running simultaneously, coordinating tasks that span departments or time zones. Achieving scalability requires frameworks that can schedule tasks, allocate compute resources, and manage conflicts across agents. Without such frameworks, agents risk collapsing under their own complexity. Scalability is not only a technical challenge, but an organizational one, requiring alignment of infrastructure, policies, and workflows to support the integration of autonomous systems at scale. Security risks increase when agents are introduced. Because they operate autonomously and can call external tools, they are vulnerable to prompt injection, malicious inputs, or misuse of their permissions. A cleverly crafted input could trick an agent into retrieving sensitive data, executing unintended actions, or bypassing safety rules. Securing agents requires strict input validation, access controls, and governance mechanisms. It also requires ongoing monitoring to detect suspicious behavior. Agents are powerful because they act, but this power is also a liability. Without careful design, they can be exploited in ways that simpler, more limited models cannot. Evaluating agents requires new methods that go beyond measuring accuracy of single outputs. Evaluation must test whether agents complete workflows reliably, handle errors gracefully, and maintain consistency across iterations. Benchmarks are emerging to measure robustness of reasoning chains, success rates in multi-step tasks, and resilience under stress. Evaluation also involves user studies, testing whether people find agents trustworthy, usable, and efficient in practice. Without rigorous evaluation, agents may look impressive in demonstrations, but fail in real-world contexts. Evaluation is the foundation for moving agents from experimental prototypes to production systems that users depend on daily. Industrial applications of agents are beginning to emerge, though most remain early stage. In customer support, agents manage tickets, search knowledge bases, and escalate issues when necessary. In research automation, they retrieve papers, summarize findings, and synthesize reports. In IT operations, agents monitor logs, detect anomalies, and recommend corrective actions. Each of these applications demonstrates the promise of agents to automate tasks that combine reasoning and execution. At the same time, they highlight the fragility of current systems, which may perform well in controlled settings but stumble in messy real-world conditions. Applications show both the potential and the limits of today's agent technology. The limitations in practice are significant. Agents remain experimental, often failing in unpredictable ways when faced with unstructured problems or unusual conditions. They may loop indefinitely, mismanage tools, or produce plans that are logically flawed. Their unpredictability makes them risky to deploy in mission-critical contexts without human oversight. While prototypes abound, few agents are trusted with core enterprise functions. This gap between aspiration and practice defines the current stage of the field. Agents show us what is possible, but they also remind us how much work remains to make them safe, reliable, and production-ready. As Episode 25 closes, the natural transition is to Episode 26, where we will explore reliability patterns for agents. These patterns provide the design principles, safeguards, and best practices needed to stabilize plan-execute loops, protect against errors, and ensure that agents can operate safely in production. If agents are the dream of automation, reliability patterns are the reality check, showing us how to build systems that do not just impress but endure. Agent frameworks provide the scaffolding that makes the development and deployment of AI agents possible. These frameworks offer pre-built components for planning, tool integration, memory, and orchestration, allowing developers to assemble agents without having to reinvent every piece of infrastructure. Just as web frameworks such as Django or Ruby on Rails made it easier to build websites by providing common patterns, agent frameworks streamline the creation of reasoning systems by standardizing workflows. Popular frameworks in the research and open-source community demonstrate the importance of this layer. They lower barriers to experimentation, provide templates for common use cases, and allow best practices to spread more quickly. Without frameworks, every team would build agents differently, leading to fragmentation and instability. With them, organizations can focus on tailoring agents to their domain rather than solving foundational design problems from scratch. Frameworks thus accelerate innovation while anchoring agents in more reliable and reusable foundations. Planning strategies play a central role in the effectiveness of agents. An agent that cannot plan risks becoming reactive, attempting tasks one step at a time without understanding dependencies or sequencing. By embedding structured planning methods such as chain of thought, plan then act, or tree of thought reasoning, agents gain the ability to map out steps in advance. This ensures that tasks requiring multiple tool calls or complex coordination do not collapse into incoherence. Planning also provides opportunities for oversight. Explicit plans can be reviewed, critiqued, or adjusted before execution. The choice of planning method influences the agent's character, whether it prioritizes simplicity, robustness, or adaptability. In practice, agents often blend strategies, using simple reasoning for straightforward tasks and branching exploration for ambiguous ones. Planning is therefore not just a component, but the very engine that gives agents coherence, allowing them to bridge reasoning with action in a way that is transparent and auditable. Task decomposition is one of the most practical ways agents manage complexity. Large goals, such as writing a technical report or managing a project, are too broad to tackle in one step. Agents break these down into smaller, manageable tasks, each of which can be executed in sequence or parallel. This mirrors how humans solve problems. When asked to organize a conference, one person breaks it into finding a venue, inviting speakers, managing logistics, and promoting the event. Each subtask is solvable, and together they build toward the larger goal. Agents that decompose tasks effectively are more reliable, as they avoid being overwhelmed by the scope of the problem. Decomposition also allows better error handling, since failures can be isolated to smaller units without derailing the entire workflow. This modular approach reflects a key principle in systems design. Complexity is best handled when broken down into understandable and executable parts. Human-in-the-loop agents recognize that autonomy should not mean isolation. In many real-world deployments, agents are given guardrails where sensitive or high-stakes actions require explicit human approval. For example, an agent managing financial transactions may prepare trades but require human authorization before execution. A legal research agent might compile arguments but leave final drafting to an attorney. Human-in-the-loop design acknowledges that trust in agents is built not by removing people but by integrating them thoughtfully. Oversight provides accountability, prevents catastrophic errors, and ensures that humans retain ultimate control over decisions with ethical or regulatory consequences. These hybrid systems blend the efficiency of automation with the judgment of human expertise, offering a path forward that is both ambitious and responsible. Persistence and memory allow agents to sustain workflows across time, rather than treating every interaction as a blank slate. Memory lets agents recall previous steps, track context, and learn from outcomes, creating continuity in their reasoning. Without memory, agents behave like forgetful colleagues, repeating work or losing sight of objectives. With it, they can carry context across conversations, adapt to user preferences, and refine strategies based on history. Memory also enables long-term collaboration, where agents build up institutional knowledge that makes them more valuable over time. Yet memory introduces its own challenges, such as deciding what to retain, how to store it, and how to prevent sensitive information from being misused. Designing memory systems is therefore one of the most important and delicate aspects of agent development, balancing persistence with privacy and efficiency. Coordination across agents expands the horizon of what these systems can achieve. Instead of relying on a single agent to handle all aspects of a task, groups of agents can collaborate, each specializing in a role. One agent might retrieve data, another may analyze it, while a third synthesizes findings into a report. Coordination requires clear communication, task delegation, and error handling, much like teamwork in human organizations. Multi-agent systems show promise for scaling reasoning beyond the capacity of any single agent, distributing workload across specialized processes. However, coordination also multiplies complexity. Conflicts may arise, communication may break down, and failures may spread. Designing coordination mechanisms that balance independence with collaboration is therefore critical to realizing the potential of multi-agent frameworks. Latency and efficiency issues remain constant challenges for agent systems. Every cycle of planning, execution, critique, and tool calling adds time compared to single-shot model responses. While this overhead is the price of reliability, it can frustrate users who expect speed. Agents must therefore optimize when to plan extensively and when to act quickly. Some frameworks implement adaptive loops, where more reasoning is applied only when tasks are complex or ambiguous. Others cache results or streamline tool calls to reduce delays. The trade-off between speed and robustness is central to agent design. Striking the right balance ensures that agents are not only accurate but also usable, providing reliable results without sacrificing responsiveness. Evaluation benchmarks for agents are evolving to reflect their unique characteristics. Unlike static language models, agents must be tested not only for accuracy of single answers, but for success in multi-step workflows. Benchmarks now measure whether agents can decompose tasks correctly, manage tool use effectively, and recover from failures. They also test resilience under stress, such as when tools return inconsistent results or when unexpected conditions arise. Evaluation in this context is multidimensional, incorporating accuracy, robustness, interpretability, and efficiency. These benchmarks are essential for distinguishing between prototypes that work in controlled demos and systems that can perform reliably in production. They provide the standards that guide progress in a field where enthusiasm is high but reliability remains uneven. Ethical and governance considerations become even more pressing when agents act autonomously. A system that can plan and execute across tools must be bound by policies that ensure safe and responsible use. Governance frameworks may define which tools can be called, under what conditions, and with what data. Ethical considerations may guide decisions about transparency, accountability, and user consent. For example, an agent that monitors employee activity must operate under strict privacy rules, while one that processes healthcare data must comply with medical ethics and regulations. Governance is not an afterthought, but a design principle, ensuring that autonomy does not translate into recklessness. Without it, agents risk creating new ethical challenges faster than they solve practical problems. Adaptability distinguishes agents from rigid workflows. Unlike static pipelines, agents can adjust their plans dynamically when tasks fail, tools become unavailable, or conditions shift. This adaptability is key to making agents robust in real-world environments, where unpredictability is the norm. For example, if a data source is offline, an adaptable agent might switch to a backup, adjust the scope of the task, or notify the user of partial results. Adaptability also supports innovation, as agents can explore alternative strategies rather than halting at the first obstacle. However, adaptability must be bounded by rules, ensuring that flexibility does not turn into chaotic or unsafe behavior. Designing adaptive systems is therefore a balancing act between resilience and control. Cost implications loom large in discussions of agents. Because agents often operate in loops, repeatedly calling tools and refining outputs, their computational costs can be significantly higher than single-pass models. This includes not only processing power, but also fees for third-party APIs, storage for memory, and infrastructure for orchestration. Enterprises must weigh whether the benefits of automation justify these expenses. In many cases, the cost is offset by reduced human labor, improved reliability, and faster workflows. Still, cost efficiency remains a critical design goal, pushing developers to optimize agent loops, minimize redundant calls, and cache results where possible. Cost is not a trivial consideration. It is a determining factor in whether agents remain experimental prototypes or become sustainable production systems. Research trends reveal growing interest in multi-agent systems and collaborative reasoning. These approaches see agents not as isolated problem solvers but as members of a collective, reasoning together, critiquing each other's plans, and reaching consensus. This trend mirrors human societies, where groups outperform individuals in complex problem solving. Collaborative reasoning allows agents to hedge against individual weaknesses, pooling strengths across perspectives. However, it also raises new challenges of communication, coordination, and control. Research into protocols for multi-agent interaction, consensus strategies, and conflict resolution will be critical for scaling these ideas responsibly. The promise of collaborative agents is immense, but it requires careful attention to avoid the pitfalls of disorganized collective behavior. Applications of agents in enterprises are already appearing, though often in constrained settings. Workflow automation is one example, where agents manage repetitive processes such as onboarding employees, generating reports, or monitoring compliance. In security, agents monitor logs, detect anomalies, and escalate threats, acting as constant sentinels. In knowledge management, agents compile research across sources, synthesize insights, and present structured outputs. These applications demonstrate the potential for agents to handle real-world complexity while freeing human experts for higher-level tasks. Yet they also reveal current limitations. Agents may work reliably for routine processes, but struggle with edge cases. Enterprises adopting agents must therefore set clear boundaries, deploying them where reliability is high, and supervising them closely where uncertainty remains. The future outlook for agents is one of gradual but steady expansion. As frameworks mature, reliability patterns strengthen, and costs decline, agents will move from experimental prototypes into everyday workflows. Adoption will likely begin in low-risk, high-volume tasks, where errors are tolerable and oversight is feasible. Over time, as confidence grows, agents may handle more critical roles, though always under governance and monitoring. The trajectory suggests not a sudden revolution, but a steady evolution, as organizations build trust in agents step by step. The promise is immense, but it must be realized through careful design, responsible deployment, and relentless focus on reliability. The natural bridge to Episode 26 is the topic of reliability design patterns. While Episode 25 has shown what agents are and how they function, Episode 26 will examine the concrete strategies that stabilize them in practice. Reliability patterns ensure that plan-execute loops do not spiral out of control, that hierarchies remain coherent, and that task queues are processed safely. They are the missing link between prototypes that impress and systems that endure. Without reliability, agents remain fragile. With it, they can ship and stay in production. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.